Welcome to this exploration of converging lenses. These fascinating optical devices play a crucial role in how we focus and manipulate light. Throughout this presentation, you'll discover how converging lenses work and why they're essential in everyday technology. A converging lens, also called a convex lens, has a distinctive shape. It is thicker at the center and thinner at the edges. This unique curvature causes parallel light rays to bend inward as they pass through the lens. All these rays converge, or come together, at a single point called the focal point. The bulging out shape is what gives the lens its ability to bring light together. Let's understand some important terminology. The principal axis is an imaginary line passing through the optical center, perpendicular to the lens surfaces. The optical center, denoted by O, is the central point where light passes through without any deviation. The focal point, represented by F, is where parallel rays converge after passing through the lens. Finally, the focal length, represented by F, is the distance from the optical center to the focal point. For converging lenses, this value is always positive. To understand how images form, we use three principal rays. First, any ray parallel to the principal axis refracts through the lens and passes through the focal point F. Second, any ray passing through the focal point F on its way to the lens emerges parallel to the principal axis. Third, any ray passing through the optical center O continues straight without any deviation. These three rays help us predict exactly where and how an image will form. The position of an object relative to the lens determines the characteristics of the image formed. When an object is placed beyond 2f, the image is real, inverted, and diminished. At exactly 2f, the image is real, inverted, and the same size as the object. Between f and 2f, the image becomes real, inverted, and enlarged. However, when the object is placed between f and o, something interesting happens. The image becomes virtual, upright, and enlarged. This is how magnifying glasses work. The lens formula mathematically relates three important quantities. It states that 1 divided by f equals 1 divided by v minus 1 divided by u here. F represents the focal length, v represents the image distance from the lens, and u represents the object distance from the lens. This formula allows us to calculate where an image will form for any given object position. Magnification tells us how much larger or smaller the image is compared to the object. The magnification, represented by m, equals v divided by u, which also equals h prime divided by h, where h prime is the image height and h is the object height. When m is greater than 1, the image is magnified. When m equals 1, the image is the same size. When m is less than 1, the image is diminished. A negative value of m indicates that the image is inverted. Converging lenses are everywhere in our daily lives. Cameras use them to focus light and capture sharp images. Eyeglasses with converging lenses correct hyperopia or farsightedness. Microscopes use these lenses to magnify tiny objects for scientific study. Telescopes gather light from distant celestial objects. A simple magnifying glass enlarges small text and objects. Projectors use converging lenses to enlarge images onto large screens. Understanding converging lenses helps us appreciate the technology that shapes our visual world.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.